So the topic is about quality control of synthetic small molecules by solution NMR, and how much workload automation can take off the shoulders of expert NMR spectroscopists, yeah, by automating processes. So let's start off. I hope you can see my pointer. In the glorious old days of synthetic chemistry, chemists, penciled everything into handwritten lab books, like the chemical reaction. They would have like a list of the reactants, a list of which products could come out. They have like some protocol procedure, and they even sketch some early like reaction monitoring analytics, like this thin layer chromatography in the lower left corner onto their page in the handwritten lab book. Yeah, but all more sophisticated analytical data like an LCMS or NMR or an IR or even other analytics would usually come in the old days on a separate sheet of paper, or nowadays they come electronically. They go in a separate database each, or end up electronically in a different folder on a network drive each. So for answering a simple question like, is the product of the chemical reaction sufficiently pure and has it the right chemical structure, the chemist has to retrieve data from several documents or from several folders or several applications or databases. And that could take easily up to 10 minutes just to retrieve the data from the different places. So if the chemist has to deal with like 10, 20 or even 100 chemical reactions a day, that would cost him a lot of work time, just assembling and retrieving data from different sources. So the obvious solution there would be to integrate all substance data in a single application, the electronic lab book, which most of you probably have. So you would categorize everything by the substance identifier, and then you would have like subfolders for all relevant data that belong to that substance or that reaction. That obviously is a chemical reaction with the chemical structures, but it also would be environment, healthy and safety information if you have to handle like dangerous reactants. And that would include like a subfolder for LCMS data and would include a subfolder for NMR data. So here all the information that you need and to submit samples for different techniques would be together in that single application. So if you then want, or the chemist wants to submit a reactant or an intermediate from the reaction or the product of the reactions for NMR, LCMS or chromatographic separations, it would be most convenient for that chemist if you could just do that from the electronic lab book. So we enable that by a simple system. So that's our subtable here for analytics. You just highlight, right, that row with the substance ID of, for example, that intermediate or that reactant, and then you can select in the second column the analytical technique you want to submit it to. For example, here LCMS and NMR. Then you can select in the third column here the solvent. So, for example, deuterated DMSO. And then all you need to do is just go into that little column, little box with vial identifier. You use your 2D barcode scanner, would scan in the vial ID on the bottom of this little container, yeah, and press submit, and then all the information, the data for that substance, for the analytics will be pushed on into the system. And then all you need to do is put a little bit of a spatula of your substance into that vial and put it in a separate place. So now that the data are sent off, you can look on the other side of this system, the NMR expert lab, where the analytics take place. So there we have to take care of two things. We have to handle the incoming data, as I showed you, from the electronic lab book. But we also have to think about how we can automate the substance material workflow. And that I show you in the next slides. So we have two different options. If the chemist here wishes to have both an LCMS and an NMR from the same submitted substance, we use this process where the chemical is submitted, little spatula in this 10 milliliter glass vial. The barcode is on the bottom, right? You scan that in. That gives you the vial identifier. Then those little glass vials are put here on a tablet of a liquid handling machine. And that machine balances how much material you put in the glass vial. It adds acetonitrile, dissolves the sample, and then splits the solution into two 60-well microtiter plates. So one plate for NMR analysis and the second plate for LCMS analysis. Yeah. So it has two functions, splitting the sample and secondly grouping individual samples as they have been submitted by various chemists in 96-well format. And then we put it into like a gene vac, we dry off the solvent and put it into the NMR. As I show you in more detail on the next slide. Yeah. So we dry off the acetonitrile, then we have the dried substance here in 96-well format, well aligned, one sample in each well. Then we have another liquid handling machine that adds deuterated solvent like DMSO to each well. It shakes it automatically, dissolves that, and transfers the liquid from that 96-well microtiter plate into a 96 format of NMR tubes. Yeah, in this box. So we have long thin needles. We put the liquid to the bottom of that tube in the same format. And then we transfer the whole box into the sample changer of the NMR machine. After the measurement, we just throw out the entire box of tubes. So you no longer have to put NMR tubes into spinners and put them into the sample holder one by one, but you have everything categorized in 96-well format. Yeah, you unpack your tubes, fill them, measure them, throw them out. We have a second process for cases when the chemist wants to have the NMR data measured immediately, or B, when the chemist selects like volatile solvents or wants to have additives like acid or bases in addition to the organic solvent, for example, to improve the solubility of certain analytes. In that case, he puts that little spatula of his chemical matter into this 1 millimeter vial with the barcode again on the bottom. Then he collects samples in a 96-well format again. Yeah, if you want to have it immediately, you only have like 1, 2, 3, or 10. And then you would submit it to the NMR lab. And there we have a 2D plate scanner, yeah, which scans in one row all the 2D barcodes here on the bottom of these vials. Yeah, that is a picture of that 96-well plate photographed in high resolution from the bottom. Yeah, and that drives again the liquid handling machine. Yeah, we have the position information, we have the vial identifier for each position. At the deuterated solvent, then you would transfer it into NMR tubes and in the sample changer. For the few samples that need like a volatile solvent, we do add actually that solvent like chloroform or methylene chloride manually with the positive displacement pipette, because that is then dropless dispensing. Good. So on the NMR side, we decided for using 1.7 millimeter sample jet tubes, because that reduces the sample volume to only 30 microliters and enables the acquisition of even a low sensitivity 2D carbon-13 HMBC spectrum in about 8 minutes if we have like substance on the order of like 1 milligram plus minus, or a bit more, a bit less. The sample changer is refrigerated, so the samples stay there in for like overnight or rest there for longer. They are so in solid form when it's DMSO. We have a little preheater who puts it like 10 minutes before the measurement onto measurement temperature and transfers it into the NMR shim bore and measure that. Good. So now we have all our samples in the NMR magnet sample holder. We have to think about how we record and process those spectra. So as I showed you, the data about the sample, like the owner, the date, which solvent has been selected, which NMR experiments have been selected, comes in directly from the electronic Labbook. Then we use like macros in Excel to drive the liquid handling machine, meaning add the appropriate volume of deuterated solvent, depending on how much substance mass has been submitted. And we also use the same very macros to drive the NMR acquisition through the LIMS import system of Topspin, ICANMR Topspin. So then the NMR raw data, saved as a data set named by the substance ID, are written on a shared folder, and from there the heart of that whole analysis process, here the Mastronova Verify Listener starts working. So listener works 24/7, and permanently looks for new NMR data. And whenever it finds new NMR data, it imports the proposed chemical structure from the electronic Labbook, and compares the experimental NMR data with the predicted NMR data based on the proposed chemical structure, does an automatic structure verification, and writes the analysis of these structure verification into the MNOVA database here. And from there we extract key information such as purity and the chemical structure verification score back into electronic Labbook. So it's like a closed system, right? The data start off by submission from the electronic Labbook, and the chemist gets the results of that analysis back into the electronic Labbook, where he can see it and view it, as I show you in a second. So here is like a close-up of how that MNOVA Verify Listener works. So you get a log file written as a text file on a folder that you can select, and you get information whether new data have been recognized, whether new data have been processed and have been written to the database. And that works permanently, just a random recording, a screenshot from August this year. In the setup of the Verify Listener, you can select from which source the proposed chemical structures come. We keep them into one folder on a network drive as SDF format, but you can use MOL format or whatever else you want to use. And you can select which NMR spectra you want to record and process for each sample you submit. So by default we do like a proton, 1D proton NMR. We do a 2D multiplicity edited carbon-13 HSQC, and we do a 2D carbon-13 HMBC for each substance that is submitted. And then next, here I show you a screenshot from our electronic chemistry Labbook. So that's what the chemist would then see, and where he wants will view the data first. So it's all sorted by the material identifier, or like the substance ID, shown here, the random code generated by the system. Then the chemist will see the chemical structures here again for all of those chemicals. I have to apologize. I had to delete most of the chemical structures because it's like a screenshot for a company workbook, and I'm not allowed to share those. So it's a real screenshot from the Labbook, like end of July, early August here. So a typical chemistry project would be a synthesis of like 10, 20, whatever, 40 compounds, and they would be all have similar. So the chemist all sees the chemical structure, and there would be just a variation, the substituent on that scaffold, for example. And then, but here importantly, he gets like an immediate tabular overview of the key information from the NMR experiment, meaning a relative NMR purity, and here in this column, the automatic structure verification score. So if that number, I don't know whether you can read it, if that number is larger than like 0.5, maximum 1, then it's a high likelihood that the chemical structure is correct. that means matches the proposed chemical structure. If the number is smaller than 0.5, all the way down to 0, it is very likely that the chemical structure is wrong, or something in the data analysis couldn't be handled and needs manual analysis. Yeah. So guess you have now whatever 20 or 50 chemical structures here in a table. You could sort your table, by the size for the number of the verification score, or also for chemical purity, and you could focus on your attention at samples which have like a insufficient chemical purity, or which have a poor structure verification score. And usually that might be 5%, 10% of your samples, and then you would can follow up those samples in more detail. And that works as follows. So also in that third column here, we provide a link that directly opens, if you click on that, directly opens the NMR data automatically analyzed in the MNOVA application. And I'll show you that on the next slide. So here again, that's the display, default display, how we roll out MNOVA to our customers, to our chemistry clients. So we show the automatic structure verification score up here. We show the relative purity for the NMR up here in that window. And then we have obviously the free NMR spectra record, like the 1D proton spectra, the HSQC, the HMBC in individual pages, all in one document, well sorted and grouped together. And we have the chemical structure. And that has highlighting for all the signals and chemical groups which could be well analyzed automatically. They have like a green circle around. And you also see some signals which couldn't be assigned here to atoms on that chemical structure, which are highlighted here in red, or if they're ambiguous, they're highlighted in yellow or gray. And that helps the NMR expert immediately to focus attention to that part of the molecule which has issues. For example, these methyl link groups here of the piperidine ring, here on the scaffold in the middle, which may be affected by chemical exchange, may be very weakened. So the automatic software, MNOVA Verify Listener software, couldn't, for example, pick them or find them, or the signal to noise was insufficient to find the peak at all, or maybe overlapped with the strong water signal. So these are the issues where you have to look at and focus your attention. And you don't have to care very much about all the signals which are in green, which are most of them, because they could be found and identified and analyzed very easily by the software. That simplifies the life of the NMR expert. He doesn't need to spend much time on the routine business of analyzing all the signals, integrating and multiplicity editing them. And the second major advantage of a fully automated analysis system is that it makes it easier and more amenable for analysis for non-expert NMR users. So the average chemist, synthetic chemist in our labs wouldn't have a full NMR training, and would struggle with in-depth NMR analysis such as phasing spectra or deconvoluting overlap peaks and stuff like that. That would be too difficult, and that makes sense that it's taken over by the software. But what those chemists can do very well is just counting. Counting the hydrogen integrals in the 1D proton spectra and comparing it with the number of hydrogen atoms in the proposed chemical structure, and also counting the number of CH, CH2, and CH3 signals in the multiplicity edited 2D HSQC spectra, and comparing that to that corresponding number of atom groups in the proposed chemical structure. So reduce a very difficult task to just a counting business for most of the signals on the molecule. And that is very much amenable to synthetic chemists with some training in NMR, but doesn't need like in-depth analysis of multiplicity structures. It doesn't need in-depth analysis of experimental chemical shifts compared to predicted chemical shifts, with deviations from chemical shift predictions, jobs which are much more difficult than just comparing the number of signals between the expected expectation from the chemical structure in those spectra. And then thirdly, we asked like the expert user just to look for like well-resolved characteristic functional groups in the HMBC, such a carbonyl group or carbon fluoro coupling, or checking whether like an ester is still in place by checking whether you get a correlation to the carbonyl of the ester function. But that's about it. So we don't ask the average chemist to analyze like chemical shift matching or multiplet structure and all those much more sophisticated information you can get from your NMR spectra. And once you have all that set up in an automated process that runs 24/7, you're all set to process and analyze NMR spectra from several spectrometers within your company, but you can also process and analyze NMR spectra or NMR data from suppliers of chemicals. You can do that for automated synthesis systems. So in-house we have like a parallel synthesis machine that does libraries of compounds in 96-well format. So you get like always blocks of up to 96 chemicals for analysis each. It's already pre-plated, and you can feed it directly into this automatic processing and analysis system. Also, you can think about doing like a shelf life quality control for like libraries of compounds, such as 100 or 1,000 compounds. You want to check whether they're still like in solution, have the right concentration, and haven't been decayed or anything. Yeah. So once the system works, it just requires a minimum of hands-on FTE time. Yeah. And only those few samples from all those that you process that have a very bad score or have a very bad purity would need hands-on expert investigation and will cost you FTE time. But if most of the samples that you get in from various sources are like pure and have the right chemical structure or give you a good score, then you wouldn't need any FTE time, and you could process easily hundreds, even thousands of samples by that setup. And with that, I'm ready to summarize what I've told you. So integration of analytical data into electron labbooks accelerates and facilitates data usage, including the usage of the NMR data. So analytics on packs of more than 50 substances from, for example, libraries, from reactant collections, if you do reaction monitoring matrices or external suppliers, becomes feasible without significant extra workload. Partial automation of NMR sample preparation in 96-well plates works in the routine lab setting rather than doing individual NMR tubes one by one, and saves you some hands-on FTE time. So whenever you have more than 10, 20 samples at a time, that makes a significant time saving. And automatic structure verification, as I showed you by MasterLab's Verify Listener, correctly assigns roundabout or average number of about 80% of the NMR signals. And it saves you substantial workload compared with manual or semi-automated processing and assessment, because it highlights those functional groups or signals which are missing, overlapped, or problematic, and it deals with the easy, assignable, easily predictable signals automatically. And getting a rough estimate of the question whether the chemical structure is correct and whether the relative purity of the sample is alright, directly into electronic Labbook enables the chemist to have like a tabular view for packs of substances and speeds up time for the chemist, who then doesn't have to look at the raw NMR data, doesn't have to look at the raw mass spec or LCMS data any longer, and just looks at the final purity number or structure verification score for most of the samples, and only has to look and deal with those few samples which have a bad score and are probably problematic. And with that, I thank you very much for your kind attention, and I'm happy to address your questions.